Hello everyone, welcome back to my YouTube channel. Today we'll be starting a new topic of Class 9 Science Part 1, that is chapter number 2, Work and Energy. So in this chapter, we will be studying the following topics. The first part of the chapter will be of work. So we'll be discussing what is work and how do we calculate work mathematically. What are the units of work and types of work. Second part of the chapter is energy. Here we'll be discussing what is energy, forms of energy, units of energy, two main types of energy, that is kinetic energy and potential energy, and the last thing, that is transformation of energy and the law of conservation of energy. And third part of the chapter is consists of two topics. First is free fall and power. Now both the topics are just an introduction. So and the last we are going to discuss numerical after covering each topic. So before starting with today's topic, if you find our videos interesting and helpful, do like, share and subscribe our channel. So let us start with today's topic. So just observe the following videos. Okay. First, there are 6 videos here. So if you observe here, you can see the boy is kicking the football. Next, he's doing skating. Next, the two people are lifting up the box. Next video, you can see they are cutting vegetables. Next, you can see two boys are cycling. And next, you can see they are playing seesaw. So when you observe all these activities which are done, what do you think? What they are doing? So they are not doing nothing but some work they are doing. Playing football, playing cycling, playing seesaw, cutting the vegetables, lifting up the box. So this is nothing but a work, some work they are doing. So to do this work, what they require energy. When they spend energy, then only they can do the work. So I can say work and energy, both are related to each other. So how they are related to each other and how they are different from each other, that we are going to see in this chapter. So today's part, we're going to study about work. So let us study about work. Generally, any mental or physical activity is referred to as work. When we walk or run, the energy in our body is used to do the necessary work. We say that the girl who is studying is working or performing work, but that is nothing but a mental work. In physics, we deal with physical work. So work has a special meaning in physics. So here we can say work has two things. First is you can do work mentally. Second is physically also. And for doing work, we require some energy, which is spent from our body. But in physics, we only deal with the physical work. It has a special meaning in physics. So let us see how we can define work in terms of physics. So in terms of physics, work is said to be done when a force applied on an object causes displacement of the object. Force applied causes displacement of the object. Let us see in this picture. So here the person is applying a force on that object. So this is the force applied by the person. And due to this application of force, the object has moved a certain distance, that is d, or you can represent it as s also. Okay. So whenever we apply force and the object moves at a certain distance s or d, we say that we have done a work. A work is done. Okay. Here also you can see one more example. Here the person is applying a force on the object and the object will move a certain distance d. Then we can see that this person has applied a force. This person has done a work. Some work he has done. So I hope you have understood the basic concept of work. Now let us see this picture. Here the boy is lifting up the object. So for lifting up the object, he is applying a force, the force by the person. So this is the force applied by the person to lift up the object. And now he is going to displace the object. So there is a displacement of the object. Also, there is one more force acting on the object, that is force of gravity. Gravitational force, which is pulling downwards the box as well as the person. Okay, so he need to apply such a force that the box will move. Now, on the box, there are two forces applying. One is the force of gravity. So that force of gravity is keeping the box on the ground, because it is the force of gravity is acting towards downwards. So due to this force of gravity, the box is at the ground, on the ground. But as the person wants to lift up that object, so from that person, the force applied by the person should be more than the gravitational force, right? So that force should be more than the gravitational force. Then only the object will be lifted up. So here I can say that the person has done work against the gravitational force, because the gravitational force is acting on the box, which is pulling the box towards the ground. But the person has applied the force to lift up the object. So I can say the person has done a work against the gravitational force. Now, mathematically, how we can define work? So work is defined as a product of component of force in the direction of displacement. This is very important. Component of force in the direction of displacement. So wherever is the displacement of the object, in that direction, whichever component is of the force, that we will consider. And magnitude of this displacement. Magnitude. Okay. So mathematically, we can write work is equal to force into displacement. So F into S. Now this force is nothing but that component of force which is in the direction of the displacement. Now, this formula can be used to calculate the work done on an object when the displacement is in the direction of applied force. But if the displacement is not in the direction of applied force, how do we calculate the amount of work done? For example, in the previous picture, you can see here, force applied linearly, that is in straight line, and also the displacement is also in straight line. So here the direction of force as well as direction of displacement, both are same. Similarly, here the force is applied in this direction. Also displacement is in this direction. Both are, the direction of both force and displacement is same. So in this case, we can apply this formula, F into S. But when the displacement is not in the direction of applied force, then what we can apply? Which formula we have to apply? So is there any different formula? So the answer is yes, there is a little change in the formula. First, I will explain you what is the difference between displacement in the direction of applied force and displacement not in the direction of applied force. So this is the first case. So this is the case 1 and this is case 2. Let us discuss first case 1. Okay. Now in case 1, what you can see. So here you can see the child is applying force on the box in this direction. So this is the force applied by the child. As you can see, he's applying the force in this direction. And when he apply the force, due to application of force, the object will move. Where the object will move? In this direction. If you observe, the direction of force and the direction of displacement of the object, both are same. So here the direction of force as well as the direction of displacement are same. So here I can use work is equal to force into displacement, this formula. But let us discuss now case 2. Now case 2, the child wants to move this vehicle and the vehicle is attached to a thread. Now he's applying the force on the thread. So he's applying the force on this thread. So this is the direction of the force, you can see here. Here the direction of the force was a straight line. But here the direction of the force is not a straight line. It is at a certain angle, right? So this is my application of force. Now you can see, though my application of force is at a certain angle or it is not a straight line, then also my object, this is my object which on which I am applying my force. This is moving in a straight line only. So direction of displacement is straight line only. So in case 2, you can see that the direction of force is not a straight line, though the direction of displacement of the object is a straight line. So here the direction of force and direction of displacement are not same. The direction are not same. So in this case, which formula we are going to apply? Same formula, force into displacement? No. For applying this formula, we have mentioned that it should be product of component of force in the direction of displacement. Is this force in the direction of displacement? No. So we cannot apply this formula. So now we have to discuss a new derivation. So for that, we need to discuss a derivation. So we are going to derive a formula when the direction of displacement and the direction of application of force are not the same. Okay. So here is our diagram. So here you have one box and I've applied a force at a certain angle. Here, as here you can see the direction of force. This is my direction of force and this is direction of displacement. Both the direction are not equal. Okay. Now here comes the concept of vector. Okay. Now, for example, before going to this derivation, let us say this is my object. I am applying a force here of 3 Newton. And from opposite side, I am applying a force of 5 Newton. So can you tell me where the object will move? In left side or right side? So of course, the object will move towards the left side because the force applied from the left side is more. This force is more than this force. This is also more, but this force is much more bigger than 3 Newton. So of course, the displacement of the object will be here. Now, what is the resultant of the force? Resultant of the force means by how much force the object will move. So from here, I'm applying 3 Newton. From here, I'm applying 5 Newton. If I was applying 3 Newton from left side, 3 Newton from right side, the object will be stationary because from both the sides, equal and opposite force are acting. So here the resultant force will be 0 because the object is not moving only. In this case, when applying 5 Newton from right side and 3 Newton from left side, so here I can see the resultant force is 2 Newton because this 3 Newton and here it will be 3 plus 2. This 3 Newton and this 3 Newton will get cancelled and the remaining additional part here is the 2 Newton. Because of this 2 Newton, the object is moving in the left direction. So here my resultant force will be 2 Newton. So taking consideration of this concept, here, this is my object and I am applying a force here. Now this is my resultant force, you can say. This is nothing but resultant force. Okay. Now I have to divide this resultant force into 2 components. How many components? 2 components. If I say I'm applying a force in this direction towards right, this is my force 1. And another force I'm applying in upward direction, this is force 2. What will be my resultant? Resultant will be somewhere in middle of this force between these 2 forces, right? Same way, now this is my resultant. This is in the diagram which I have drawn. This is my resultant and I have to draw the 2 components. So how I can draw the 2 components? So one component will be like this. Other component will be like this. I will name this component as F1 and this component as F2. And this is nothing but by the resultant of the 2 components. So here you can see my first component will be in right direction and second component will be in upward direction. Okay. So this component is nothing but the component which I have shown you in previous diagram, which I have drawn. So what we have done, we have just shifted this component here. Okay. So there is a different theory here, like when you represent a vector, this is my vector. So you can shift the vectors from one position to another if and only if the direction as well as the magnitude remains the same. So here we have drawn a vector at this position. I can shift this vector here also with same magnitude and same direction. Here also, at this position also, the vector was in upward direction with same magnitude. And if I shift it here, here also the vector has same direction, same magnitude. This is nothing but concept of free vectors. Now, the concept of vectors, direction, magnitude, these are you will learn in higher standards. For now, you have to just understand that there are 2 components of the force. One is at the x-axis direction, one is at the y-axis direction. Okay, let us name these components. One is fx. You can also name it as f1, f2. I have represented as fx and fy because first force is acting along x-axis, second force is acting along y-axis. So I have now two components. First is fx, second is fy. You can draw any there. So this is my fx and this is my fy. Okay. Now, where is the direction of displacement? Then my direction of displacement is like this, as you can see in the figure. So I can say that the direction of displacement and the direction of x component of the force both are same, right? Direction of displacement and direction of x component of the force both are same. So here I can say work done is nothing but x component of the force into displacement. Now this is my new formula. Previously, when the direction of force and the direction of displacement were same, we said that work done is nothing but force into displacement, right? Here I am saying work is nothing but it is a product of force, component of force in x direction on the x-axis into displacement. Now what is this fx? Now we have to solve this fx first. Then we'll modify our formula. Now to solve this fx, now we will just derive this formula. First we will write the description of the diagram. What do you mean by f? What is fx? What is fy? What is d? First we'll explain the components. So here I will start my derivation. So point number one, let F be the applied force. Let F be the applied force and Fx be the component of force which is in the direction of displacement. Then we will define what is D. You can put this for instead of D, you can also put S for displacement. So in the diagram, I will just make a change here. I will put S here instead of D. Okay. Second point will be what is S here. So let S be the displacement. Okay. So with the help of these 2 points, we have described the diagram. Let F be the applied force to the object, Fx be the component of the force which is in the direction of the displacement, and S is the displacement of the object. Right? Now, third point, what we can write? Work done. We want a derivation for work done. So we can write that work done is given by what is a formula for work done? Product of component of force in the direction of displacement and magnitude of displacement. Now here which component of the force is in the direction of displacement? That is a Fx. So here I can write Fx into magnitude of displacement, that is S. So this will be my formula. W is equal to Fx into S. Now I will name this equation as equation number 1. Now we will do the further derivation to solve for Fx. What is exactly this Fx? So for solving Fx, now as you can see, I've applied the force at a certain angle and that angle is nothing but theta. So I will name this angle as theta. So here I can see this is my angle theta. Okay. So in the derivation also you have to explain that let theta be the angle formed between the formed with the horizontal component. Okay. So theta is the angle formed with the horizontal component. Now, here we will apply some basic knowledge of trigonometry. So before applying the knowledge, I will just explain you. Now here I have a triangle form. This is my direction of force. This is Fx and this is Fy, right? So here I have a right angle triangle form. The side opposite to right angle, it is known as hypotenuse. And this is my theta. Side opposite to angle, it is known as opposite side. And this is known as adjacent side. So this is our hypotenuse, this is opposite side, and this is adjacent side. Now sine theta is equal to opposite upon hypotenuse. Cos theta is equal to adjacent upon hypotenuse. And tan theta is equal to opposite upon adjacent. So these are the three basic formulas. One is sine theta is opposite upon hypotenuse. Second is cos theta, that is adjacent upon hypotenuse. Third is tan theta, which is equal to opposite upon adjacent. Right? Now here, as you can see in the diagram, which component we want? We want the component which is in the direction of displacement, that is Fx. Now Fx is which side? Adjacent side. So which formula we will take? In which there is an adjacent side included. Okay, do we want this opposite side? No. So the preferred formula will be this one, that is cos theta is equal to adjacent upon hypotenuse. We don't want opposite side. We want only the side which is in the direction of displacement, that is Fx. So with this knowledge, we'll apply here trigonometry in our derivation. So we'll write by trigonometry. So from the figure, we can say cos theta is equal to adjacent upon hypotenuse. In your book, it is in a base upon hypotenuse. You can say base upon hypotenuse also. Cos theta is equal to adjacent upon hypotenuse. Now, which is our adjacent side? Our adjacent side is Fx, that is equal to Fx upon F. Hypotenuse is our resultant force, that is F. So cos theta is equal to Fx upon F. So what we can write for Fx? Therefore, Fx is equal to F into cos theta. Okay. Now we'll substitute this Fx in equation 1. So equation 2, substituting 2 in 1. So we'll get W is equal to, in place of Fx, we'll substitute F cos theta. So F cos theta into displacement. Finally, we can write W is equal to F into S cos theta. F into S cos theta. So this is our formula for finding the work if the direction of force and displacement is not the same. So what is the additional thing here? That is a cos theta. This angle which is formed between the resultant force and the component of the force in the direction of displacement. Now let us discuss some cases so that the concept of work done will be clear to you. Okay. So here I'm taking an object. So this is my object and I'm applying a force to an object in this direction. This is my applied force. Now, in this case, I'm taking the direction of displacement of my object in upward direction. So this is my direction of displacement of my object. Now, when I resolve the force into two components, I will get here the first component as my horizontal component Fx and second component as vertical component, that is Fy. So here I'm getting two components Fx and Fy. In the previous example, we took this horizontal component, that is Fx, and we defined work as work is equal to Fx into displacement. Now here, since the direction of displacement is upward direction, we will take that component of force which is in the direction of displacement. So here I can see that my direction of the displacement is in upward direction, and in the same direction, my direction of the vertical component is there. So now here I will take that component of force which is in the direction of displacement, and that is Fy. So here I will write work done is equal to Fy into displacement. See here, the component of force will be Fy because that component is in the direction of displacement. But here also the formula remains the same, that is Fs cos theta. Let me explain you. Now what is theta? Theta is the angle which is formed between the resultant force and the component of force which is in the direction of displacement. Now here our resultant force is this one, and the component of force which is in the direction of displacement is Fy. So here the theta will be this angle. Okay, so here my theta will change. So again, if I apply trigonometry, this is my hypotenuse, this is my opposite side, and this is my adjacent side. So again, I can write cos theta is equal to adjacent, which is adjacent side Fy upon hypotenuse, and hypotenuse is F. So again, if I substitute for Fy becomes F cos theta. So again, my formula becomes the same. W is equal to F cos theta into S or Fs cos theta. So whenever you're solving the numerical, you have to apply the same formula. Work done is equal to Fs cos theta. But you need to check which is the angle. So your angle is nothing but it is between the resultant force and the component of force which is in the direction of displacement. So angle can change from case to case. Similarly, if I tell you the second case, this is my object and I am applying a force on that object in this direction, and my displacement of object is also in the same direction. So here the angle formed between force and displacement is 0 degree. So here my theta is equal to 0 degree. There is no angle between force and displacement. Even in this case, I can apply the formula work done is equal to Fs cos theta. Now if I substitute the value of theta as 0, I will get Fs cos 0 degree. And the answer of cos 0 is equal to 1. So I will directly get work done is equal to force into displacement. So conclusion part is that work done is equal to Fs cos theta. This is our general formula. So this is our general formula. From this formula, you can calculate the work done for any cases. You just need to find the theta. If theta is 0, then you will get F into S. If theta is 90 degree perpendicular, then you will get work done is equal to 0. So one more thing you should remember, if theta is 0 degree, work done will be maximum. And if theta is 90 degree, then work done will be 0 or minimum. Okay. So this is the conclusion part. So I hope you understood how we have derived the formula for work done. Now let us discuss about unit of work. So what is work? Work is force into displacement. What is force? Unit of force is Newton. Unit of displacement is Newton. So a unit of work becomes Newton meter. Okay. Now, what is 1 Newton? Force unit is Newton. Okay. What is 1 Newton? 1 Newton is kilogram meter per second square. Right? We have seen in this chapter number 1 laws of motion. So 1 Newton is nothing but kilogram meter per second square. So I can write for work done. Instead of Newton, I will write kilogram meter per second square into again distance meter. So finally, I'm going to get work done is nothing but kilogram meter square per second square. Okay. So for work done, I have first unit as Newton meter, or you can write kilogram meter square per second square, or you can write joule. This is what joule. So 1 joule is nothing but important thing. 1 joule. 1 joule is nothing but Newton meter or kilogram meter square per second square. Okay. In chapter number 1, we have learned that 1 Newton is nothing but kilogram meter per second square. This is 1 Newton. Similarly, 1 Joule is nothing but you have to multiply 1 Newton into meter. Force into displacement. This is unit of force into displacement meter. 1 Joule is kilogram meter square per second square. 1 Newton is kilogram meter per second square. Now let us discuss about CGS unit. In CGS unit, so in CGS unit, work is equal to force into displacement. In CGS unit, for force, the CGS unit is dyne into for distance, CGS unit is centimeter. So my work becomes 9 centimeter in CGS unit. Okay. Now one dyne is equal to gram centimeter per second square. Right? So my CGS unit for work done will be gram centimeter per second square into centimeter for this displacement. So I will get gram centimeter square per second square. And this is nothing but equal to 1 erg. This is nothing but equal to 1 erg. So conclusion is, for work, we have 2 units, SI unit, CGS unit. First unit is Newton meter. Here you have dyne centimeter. Second, kilogram meter square per second square. Here you have gram centimeter square per second square. And third one, this is nothing but called joule, 1 joule. And this is nothing but called 1 erg. Okay, so these all things you have to remember. Now we will see what is a conversion, unit conversion. How many joules is equal to how many ergs, or how many ergs is equal to how many joules. That we are going to see now. So now let us discuss about the relationship between joule and erg. Now we know that joule is nothing but equal to Newton meter. So Newton into meter. Right? So 1 joule is nothing but 1 Newton into 1 meter. Now I want relationship between joule and erg. Right? Now erg is a CGS unit of work. So I need to convert this Newton meter is into CGS unit. Now, before converting it, let us discuss one thing. When you have to convert meter to centimeter, what is the factor? Now 1 meter is nothing but equal to 100 centimeter. So I can write 1 meter is equal to 10 raised to 2 centimeter. Okay. If you want to convert centimeter into meter, same thing, 1 centimeter will be equal to 10 raised to minus 2 meter. Okay. 1 meter is 10 raised to 2 centimeter, 100 centimeter. 1 centimeter is 10 raised to minus 2 meter, that is 0.01 meter. Okay. So this is the unit conversion. Similarly, if you want to move from Newton to dyne, so 1 Newton is equal to 10 raised to 5 dyne. This you have to remember, important thing. Okay. So these two unit conversions now we will use in this. So in place of 1 Newton, I will write 10 raised to 5 dyne. And in place of 1 meter, I will write 10 raised to 2 centimeter. Now, my units are converted from SI system to CGS system, dyne and centimeter. Now, I hope you remember there is a property in indices. 10 raised to 5 into 10 raised to 2 we have to solve. We have the property a raised to m into a raised to n is equal to a raised to m plus n. That property we are going to use here. So this 10 raised to 5 into 10 raised to 2 will be equal to 10 raised to 5 plus 2, that is equal to 10 raised to 7. So here I will get, after solving this, 10 raised to 5 plus 2, that is equal to 10 raised to 7, and the unit dyne centimeter. Dyne centimeter. Now remember what we have learned. What is dyne centimeter? 1 dyne centimeter is nothing but 1 erg. So I can replace dyne centimeter into erg. We have discussed now only that Newton meter is nothing but 1 joule. 9 centimeter is nothing but 1 earth. So the relationship between joule and erg is 1 joule is equal to 10 raised to 7 erg. And if you want what is 1 erg in joule, so 1 erg in joule will be 1 erg will be equal to 10 raised to minus 7 joule. Okay. When you want to convert joule to erg, multiply by 10 raised to 7. When you want to convert 1 erg to joule, then divide by 10 raised to 7. This is the formula. So let us do some recap. First, we learned about the units. So work, it has 2 units. One is SI unit, another is CJS unit. So if I talk about the SI unit is joule. Joule is nothing but equal to Newton meter. Newton meter is nothing but equal to kilogram meter square per second square. Then we talk about the CJS unit. CJS unit is erg. 1 erg is nothing but 9 centimeter. And 9 centimeter is nothing but equal to gram centimeter square per second square. Then we learned about the conversion of joule to erg. So 1 joule is equal to 10 raised to 7 erg, or 1 erg is equal to joule upon 10 raised to 7, or you can write 10 raised to minus 7 joule. Okay, so this is the summary of the topic units of work and relation between joule and erg. So this is the end of today's session. I hope you understood and found this video helpful and interesting. Do like, share and subscribe our channel. Thank you.